Let's get right into it. Welcome to this explainer. Today, we're unraveling the fundamental search algorithms computers use to find a specific item hidden inside massive piles of data. I mean, whether you're pulling up a contact in your phone or querying a massive global database, speed is absolutely everything, right? Just imagine trying to find one specific word in a 1,000-page book, but there's no index. Total nightmare scenario. Well, today, we're going to solve that universal problem of data retrieval. We'll look under the hood to see exactly how computers tackle this and transform what seems like an impossible, overwhelming task into literally lightning-fast calculations. Here's our roadmap for the day. We've got the search problem, linear search is our baseline, binary search, interpolation, choosing your algorithm, and finally sorting data. Basically, we're going on a journey from good to best, starting with brute force and ending with an algorithm that actually mimics human intuition.
So, part 1, the search problem and linear search. Let's establish our baseline by looking at how we search through a totally unordered list, where we have 0 guiding rules.
In an unordered linear search, the process is, well, incredibly literal. The algorithm just hops from one item to the next, entirely sequentially. It starts right at index 0 and checks every single element one after the other, until it finally hits a match. Because there's no order to the magnitude, it can't skip a thing. Now, this sequential checking results in what computer scientists call a worst-case time complexity of big O of n. Essentially, if your target is sitting at the very end of a 1,000,000-item list, the computer is forced to make 1,000,000 individual hops just to find it. For massive datasets, that is painfully inefficient. But watch what happens when we introduce just a little bit of organization. If our data is already sorted by magnitude, an ordered linear search gets just a little bit smarter. Why? Because it knows exactly when to throw in the towel and quit early. You can see how this plays out right here. Let's say we're hunting for the number 5. The algorithm hops 2, then 3, then 4, and then it hits 6. Since the list is ascending, the second the pointer hits that 6, the search safely aborts. The computer logically knows, hey, 5 is never going to appear after a 6, so it saves us from checking the rest of the list. Moving on to part 2, binary search, divide and conquer. The big takeaway so far is that sorting unlocks much better tools. Once data is organized, we can completely abandon those slow sequential hops, which brings us to our next major evolution. If that data is sorted, we unlock binary search. This is a seriously powerful, highly efficient method that drastically speeds up retrieval using a strategy we're all pretty familiar with, having the data over and over again. Think back to that 1,000-page book. If you want page 250, you're not flipping page by page from the beginning. You're going to open it right to the exact middle, page 500, and instantly realize, okay, I can ignore this entire second half of the book. Binary search does exactly this. It continuously finds a midpoint, compares it, and adjusts its boundaries. To do this computationally, the algorithm sets up pointers. It grabs the index of the first element, the index of the last element, and mathematically calculates the exact dead center midpoint between them. Then, it compares our search term to whatever happens to be sitting at that middle index. Now, if our search term is greater than that midpoint, the first pointer shifts completely past the middle. Boom, just like that. The algorithm instantly eliminates half of the remaining data in a single step. It is just a relentless cycle of dividing and conquering. And this continuous halving gives binary search a worst-case time complexity of O log n. What does that actually mean for us? It means what would have been 1,000,000 painful sequential hops in a linear search turns into just a handful of lightning-fast comparisons. It is an absolute game changer. All right, part 3, interpolation, the human touch. As great as binary search is, it does have one kind of glaring blind spot. It always blindly guesses the exact middle. And that leads us to our best method. Take a look at the difference here. While binary search obsessively targets the dead center, interpolation search skews its midpoint. Think about it. If you're looking for the number 2 in a list of 1 to 100, your human intuition says to check near the beginning, right? Not the middle. Interpolation search uses a mathematical multiplier to beautifully mimic that educated guessing, putting us way closer to the target on the very first try. And here's the real-world impact. Say we're searching for that number 2. Because 2 is obviously at the low end of the spectrum, interpolation search calculates a skewed midpoint and nails it in a single calculated leap. Meanwhile, traditional binary search completely wastes its time checking the middle first, taking 3 whole attempts just to find the exact same number.
Thanks to those highly educated guesses, the time complexity drops to an astonishing O log n. Honestly, for massive, evenly distributed datasets, interpolation search is just the undisputed champion of efficiency.
So, part 4, choosing your algorithm. Let's take a step back for a second and see how these 3 stack up head to head. Looking at this matrix, I really want to draw your attention to the prerequisites column. While interpolation and binary searches offer that explosive, mind-bending speed, they strictly demand that the data be sorted beforehand. Without sorted data, we're stuck in the slow lane with linear search. Which brings us to part 5. Next up, sorting data. Knowing that sorting is the ultimate mandatory prerequisite for unlocking all this speed, we kind of arrive at a final conundrum. And here is the million-dollar question. We know how to search fast now, but how do computers actually take these massive, totally chaotic arrays of raw data and organize them perfectly in the first place? What algorithms are doing that heavy lifting? Just think about the sheer processing power it takes to organize the world's information before you even type a single letter into a search bar. That's exactly what we'll be decoding in our next explainer. Until then, keep questioning the systems running right beneath your fingertips.